All right. Might as well get going. Boy, low turnout today. Well, that's the way it goes, I guess. So let's see. We've got, first of all, I happened to just find this on Reddit. Why programmers work at night. You guys, a lot of you guys work like late into the night, right? And there's this article is really good. In fact, if you go to Reddit/r/programming, you'll find it on there. It's like the top, but you can probably just Google why programmers work at night. I just glanced over the article, and it's interesting. So he was talking about normal schedules. If someone disrupts you, right, and you're like doing something, and someone disrupts you, well, you can get back on track pretty quickly, right? Like you can get back on track. Maybe 10 or 15 minutes, you're like back on track. Sometimes. But if you're working on a hard programming problem, and you want to keep all of that in your brain, and someone distracts you, sometimes it takes like an hour or two to get back into the groove. You'll find this out if you ever become like programmers at a company or whatever. Like if you get disrupted during your day, it can like throw you off for like an hour or two before you like get back into it. There's some really good comics about it too. But anyway, this was talking about that. So thought I'd throw that up there. I was talking to a couple of you guys. So the trip I went on, it was a conference about how to teach computer science in general. It was all about the teaching of computer science. And I heard a really interesting talk by the guy who wrote your book. It was all about kind of how he ended up writing these books and what he's talking about these days, and it was kind of cool. And he also talked a little bit about AVL trees, and he said, I really like to teach them, and I think you should still teach them. And I talked to him later, and I said, yeah, I still teach them from your book, so there you go. Anyway, if you hate AVL trees, I can give you his email address. But then I also learned about testing, and I went to a whole bunch of talks where people said, you can't give your students all the tests for their code. You have to make them write their own tests. And I thought, well, that's not what I do. I give you guys a lot of tests for these. I mean, you have to do the stuff. And what I can say about you guys, and I think tough students in general, boy, you guys are perfectionists, aren't you? Like a lot of you guys, and there's nothing wrong with that, except you do have to kind of know when to be like, OK, I've spent all the time, and I'm going to go to bed, even though it's 5 in the morning. But maybe some of you guys don't work all night. I don't know. But there's a thing called unit testing, and there's this guy who gave an interesting talk about this testing framework. You can build tests into C++ using a library, and the library is hard to use, and it's not intuitive, and it's not the kind of thing you want to throw at relatively novice programmers. This guy wrote another like wrapper around that, a program that uses it called UNC, and it actually allows you to make tests pretty easily. So unfortunately, I don't think I'll have time to do it for your class, but maybe next year in the future I'll implement it. Who knows? But we'll see. All right, let's see. Today's class. Here's what we're going to do today. We're going to talk about these things called priority queues. I'll introduce those in a minute. Homework 4. A lot of you guys didn't believe, based on my inbox this morning, a lot of you guys didn't believe me that this would be a hard assignment where it would take a long time to like get it right. So next time, believe me when I say that. I think the homework 4 was probably the second hardest assignment you'll do. The next assignment, which actually is going to be due like well after break, like a week or so, week and a half after break, is actually much more manageable for some people. And I've been looking over some of the midterm reviews, and some people said that they'd like to build their own programs a little bit more. So the next assignment, you actually get a chance to do something from scratch. So partially, anyway. Like you write like 3 different mini programs, and 2 of them are from scratch. So you'll get to do that. Let's see, midterm exam. I hope it went all right. Hands raised if it was OK. All right. No, some people, uh-oh, that's not as many as in the other class. Hope you guys did all right. I know it was long. Hands raised if the recursive function was OK, or if it was hard. Recursive function was hard. Yeah, all right. Too long? Yeah, how about you got really upset that I put like the question on one side of the page and the answer on the other side? You had to do the answer on the other side of the page? Yeah, that I apologize about. I totally didn't even think about it when I printed it out, so sorry about that. I should have ordered the questions properly. But anyway, we are in the middle of grading it. The TAs and I got a little bit of a late start grading it because I was gone. So I'm going to try to push for the end of the week when we get it back. I'm sorry it's not going to be sooner than that, but that's when we'll do that. A couple people still, like there are a couple stragglers who need to take it for various reasons. So don't talk about it too much yet. I will go over part of it, at least probably on Wednesday. All right. Any other comments on the midterm? I think the good news is that nobody left early, from my perspective. Like I kind of am like, I want people to work up. But the bad news is if you were all like rushing at the end, I feel a little bad. So I'll try to do a little better on the final. OK, here's what we're going to do. After we're going to talk a little about the Unix tip of the day, and then I'm going to flip the order of these things around. We're going to talk about these priority queues, and then at the end, I think we'll get done with that a little bit early. I will show you how to use a little bit of how to use GDB itself. In hindsight, I probably should have showed you before this assignment, but anyway, you'll get to use it for future assignments if you want to. OK? Any other comments before we get going? OK. Who has done a README file and gotten points off because of like misspellings? The TA's like, make sure you spell check. Anybody? Oh, nobody in here? Oh, that's nice. You guys know how to use a spell checker, I guess. Turns out there is a spell checker on the Linux, the homework server, that allows you to do spell checking right there if you want to. It's actually kind of cool. It's called aspell. And here's how it works. Let me show you. Let's see. We're going to homework, and then aspell -c, and then what did I call it? Is that what I called it? There we go. Declaration of Independence.txt. All right. Sorry, the text is a bit small. Let me see if I can make it a little bigger. I don't know if that helped much. But what you can do is it goes through, and it will just go through your thing and then highlight the words that it finds that are misspellings, and it gives you choices. I don't know why it didn't. I don't know why it picked up as usurpations isn't correct, but then it gives you usurpation and usurpation apostrophe. I'm not sure why it did that. What's really weird is that it picks up the next one, I think, as well. Let's see, if I hit ignore, it'll go to, oh, that's also usurpations. Disillusions, it didn't quite get that. Here we go, neighboring. Is this a correct spelling of neighboring? It actually is, especially if you're from like a Commonwealth country or something. But this speller, the spell check uses a built-in dictionary that you can actually print out. If you want to see all the words, I forgot to look it up where it is, but maybe I'll remember by next time and show you where it is. But it's just a big, long list of words. And then it gives you suggestions. Any idea what structure they might have used to hold these suggestions? A try, right? I mean, they might have. Who knows? I mean, you could actually go and look up the source code. If you really wanted to, you could. This is all. Like this program is completely open source. You could go look up the source code, and maybe they used to try. Maybe they didn't, but it wouldn't be a bad choice, I'd say. And you get some interesting choices. I mean, I'm not sure where some of these came from, right? They're definitely using some sort of heuristics to decide what choices to give you, right? I mean, neighboring, bearing, maybe it sounds a little the same, I don't know. But they'll give you some other choices, but they're probably using a try. Anyway, OK, so let's see. If we hit, let's change it to American. Let's change it to gibbering. It's one of the choices. Why not? I guess that's how they used to spell complete. But of course, most of the time, they do all right with the actual choices. OK? And you go along, and you can have it save this or not, but it will do it. You can also, let's see, B, abort. Yes. You can also do a lot of different things, like. Let's see, you can give it I think it's a language code. Let's see, is that the language? Yeah, you can give it a language. I'm not sure what the codes are, but it will pick out a language. It might have different dictionaries. You can actually give it a dictionary name if you have your own dictionary. You could do that. And then there's some other options too. But anyway, it's available to you if you want to use a spell checker. And like I said, it's open source. If you really want to go in, it's written in C. If you want to go in and see how they wrote a spell checker, why not? You can check it out. OK, kind of cool. Actually, that's been true of everything we've talked about in Linux so far, because it's all open source. If you want to go dig into the program, go for it. Right? OK, questions on the spell checker aspell? I didn't think so. OK, that's the aspell. All right, let's go into a new topic. Now, all of today's lecture is actually, we will talk about these things called priority queues. But in the end, this is all like set up for Wednesday's lecture. OK? So think of it in your head and go, why is he going into all this detail here? Part of it is because this is all like set up for the next lecture. OK? We will write a bunch of code down and do some stuff today, but you'll see on Wednesday where it all comes. You go, oh, I get it. OK? But we'll do this. So in real life, we prioritize things a lot, right? Like that's kind of a big thing. Okay, I've given lots of examples here. Emergency room, if you go into the waiting room and you've tripped and fell on your head or whatever, and you're like holding your head, right? You're going to sit there and they're going to try to help you out and whatever. And then some guy comes in and he's got like a knife sticking out his neck. Guess what? You just got bumped down in priority, right? You're going to go and they're going to go, please go sit down over here while we take care of the guy who's about to bleed out, right? And that's prioritizing. And we do this in real life in lots of situations. Professor office hours is a good one. What if I'm talking to you in office hours and a professor walks by and knocks on the door? I'll probably stop our conversation. I probably prioritize the professors over you and I talking just briefly at least to find out what he or she wants. And if she wants something long term, I'll say, can we talk later? But there's priority in that. So, I actually was sitting with a student in office hours and his phone rang, right? And he had it right on the table there for whatever reason. And the phone rang. And to his credit, he went boop and just turn it right off. And I was thinking he'd be answer it, and but no, he prioritized our conversation over his phone. And then 2 minutes later, I answered the phone, but it was it was my office phone and it never rings. I'm like, who's calling me? And anyway, but anyway, so getting on an airplane is another big one. So I spent a lot of time watching other people get on the airplane before me because they had children or they were first class or they had some other zone number. And it turns out if you have zone 2, that means you're last these days, right? You'd think, oh, zone 2, I'm going to get on kind of soon. No, everybody's in zone 1 or first class or the other categories, right? Or have kids or something. But anyway, you get lots of different ways you can get priority. So real life, priority is important. And with anything, if there's an important way of thinking of something in real life, we probably have created a data structure, or in this case, an abstract data type to think about it. Why not? We model real life with programs. So a priority queue, although it's a queue in the sense that we call it a priority queue, we're not really using a queue under the covers, although you wouldn't really want to. But a priority queue basically says, here's a bunch of things. We're going to store them based on their priority, okay? But not in any particular order. In other words, under the covers, who cares how it's built? As far as you're concerned, all you care about is being able to get things out based on their priority. Okay, that's it. There's a curtain there. Behind the curtain, you say, or you tell somebody to grab the next higher priority thing from behind the curtain. However they're lined up back there is irrelevant. Okay, this is different than all the other position-based data structures we've talked about. There's no sense of position in a priority queue. There's a sense of something has the highest priority, but there's no ordering that's going on here. In some sense, it's kind of like a stack, where there's the top element, and that's the only one you can deal with, right? So that's kind of the idea there, all right? But there's no real external idea of where in this structure it is. It doesn't actually matter. Under the covers, it matters if you want to have good asymptotic complexity, but as far as we're concerned, as far as the data or the abstract data type is concerned, doesn't matter. Okay? All right, so we'll get into some more details here. Priority queues use these things called keys. Okay? And keys are basically how you rank the objects. Okay? You compare keys to each other, and that's what we're going to use. So your thing that you're putting in the priority queue has a priority and then the data. Okay, so there's two different ideas here. You've got the priority, which is distinct. It could be related to, but it's distinct from the actual data itself. Lots of things have this. Anybody program in Python at all? Python programmers, yeah. You know the list in Python? Lists are all based on these keys, right? Well, not lists. Sorry, I lied. Dictionaries. Dictionaries are based on these keys, where you put something into a dictionary based on its key, and you store the actual value. Okay? So we use these keys a lot. And we're going to go into a little more detail than you probably care about in a minute on what keys actually are and why we care about them. Keys are not necessarily unique. You can have two objects having the same key. Okay? Here's how that would work. Let's say you have a Yelp rating. Okay? You know how Yelp rates by up to 5 points, right? Well, you could have a Yelp rating that for two restaurants that has the same rating, right? So you've got the key in that case would be the rating, and the restaurant, you could have two that have the same, and who knows which one you actually get first in your little list. All right? It doesn't really, if they're the same rating, you can't determine which one is higher priority because they've got the same priority. That's all there is about that. They can change. The keys can actually change, right? You go to the restaurant and a rat runs by you. And you go, oh, I'll go to Yelp and give them 1-star rats in the restaurant, right? Well, your rating is going to change, and so the key might change. You have to be careful about changing the key because you actually get things in and out of this data type by keys. So you can't change the key and then try to get the thing out again. You can get it out, change the key, and put it back in, but that's how the key would actually change. OK? So we're getting a little bit more detail about keys themselves. And again, I'm giving you more detail than you probably care about, but you'll see where it kind of comes together in a little bit. OK? All right, keys can actually be made by more than one value. In other words, let's say you're about to get on, let's say you're trying to go standby on a plane, right? Well, standby, who determines like who gets the highest standby? Well, if you bought a ticket that cost more, or if you bought something in first class, or if you happen to, if you happen to have like some coupon or something, maybe your priority will change depending on where that is. If you're flying standby because you happen to be a pilot and you want to go somewhere out for vacation, that's going to be a lower priority. It's going to be based on all those things. Okay, so your priority can be made by many things. Okay, you can generate your priority key from a property of the object, right? So let's say it's the price of a book. Well, you've got the book, and the property of that object is how much it costs. That might be your key. Okay? You can generate by the app, like the application can generate the key as well. So if you walk up to the counter at the airport and you say, hey, I want to do standby, well, the gate agent can go, OK, where are you going to fit in this priority list? I mean, it's all probably done in a computer, but in reality, it can be made up by all these things, and it can be generated, which doesn't necessarily have to do with the object itself. Okay? This is an interesting one. Generating these keys by the property, sometimes that doesn't necessarily, well, generating the keys in general sometimes doesn't necessarily work the way you think it should. You guys go to Amazon.com, and you search for some type of item. And the first one that comes up has like 5 stars, right? And only 2 people have voted on it. And the next one down has like 4.6 stars, but like 4,000 people have voted on it. Which one's probably the one you're going to want to buy? Right? The one with 1,000 votes where lots of people think it's the same. So I personally think that Amazon actually has it backwards a little bit. They should change their keys a little bit for ranking to have to do with like how many people actually did this. I think they may have changed it recently. Some search engines do that, where they change if there's not a threshold, they won't actually include it in the top so many votes. It needs a certain threshold to get there. So that's that. Okay? So we kind of get the idea of keys, their priorities, and they're based on a ranking. Yeah.
So in terms of application, would the application sort of be more of an amalgamation of different properties for a certain purpose? Is that not a valid definition?
No, that's fine. I mean, the application could be, the application that determines it could take the price and how many people voted on it and where you, let's say you're doing Yelp, right? The top restaurant's not going to be the 5-star restaurant in Maine. It's going to be the one that's closest to you, right? So I mean, there's properties that you can determine to make up the key. I mean, it's a little more subtle than that and how these things work. But you can make a key up from various different properties if you want. That's fine. OK, let's go on. Let's talk a little bit about keys. Anybody taking discrete math right now? Are you taking it? This actually comes from some kind of discrete math ideas, where you've got a bunch of properties about numbers that you're trying to compare. OK, these sound a little weird, but if you have keys, which are generally numbers, and numbers certainly meet this, well, integers meet this comparison guideline. Floating points don't necessarily, believe it or not. But if you want to compare two things, and it might not be numbers, so you got to think about how you're going to compare things. If you're going to compare two things, we have to have the following qualities or properties have to be true for those numbers. You have to have the property that for any number, the number is less than or equal itself. Why not equal to itself? Well, I'm not really sure, but it definitely. But I think in the general sense, the two values that are the same have to be less than or equal to each other, no matter how you actually arrange them. Okay, that's one of them. Another one is this one called the asymmetric property, which is kind of neat. If k1 is less than or equal to k2, and k2 is less than or equal to k1, better be true that k1 is equal to k2, right? And why is that the case? Well, it kind of just makes sense from the standpoint that there's no way to be less than and then still equal to something, and less than one thing and then less than the other thing, or the other thing being greater than it. So, no, sorry, both less than. All right. Transitive property is another good one here. If you've got three numbers, and k1 is less than k2, and k2 is less than k3, well, k1 better be less than k3. OK, that makes sense too. I mean, all these are fairly intuitive. Nothing like rocket science-y about them. They're fairly intuitive. If you meet all those three requirements, then you will never have a contradiction when you try to compare two numbers together. In other words, you will be able to decide whether two numbers compare favorably. Okay? We haven't talked too much about when you want to compare numbers, but we will in a couple weeks. In fact, your next homework assignment is going to be about this thing. Comparing numbers is used to sort things, right? To actually put them in order. Priority queues, we're not going to worry about the order. You'll see why. Or we're not going to worry about the order from the abstract data type part. But in this case, if you satisfy these rules, you will have correct comparisons no matter what you do. OK. If you have these comparison rules and they're sufficient, then you can define a relationship among the keys. The only things that can be out of place are identical keys. OK, so if you have two keys that are the same, it could be like A, B, C, D. And if B and C are the same, it could go A, C, B, D, just because you could flip them. All right. If you have that, then you can always say that there's a smallest one, or a smallest one that's shared between many values. But you can always say that, look, this key is the smallest key. Does that make sense? If you're able to compare all the ones, you can line them all up, and you can say that one's the smallest, no matter what. Now, they might all be the same, but that one is still the smallest. OK? Does that make sense? You'll see where this is going in a little bit. OK, so now we know that there's a minimum one. If there's a minimum one, then we can create this thing called a priority queue, OK, with that minimum one. Priority queue is the following. It's very simply a container, which we've used a million times. Right? The other containers that we have are things like lists, right? Queues, stacks. They're all containers. They hold items. Okay? It's a container, each having that associated key that's provided, each having an element with an associated key that you give it when you insert it into this priority queue. And the keys determine the priority used to pick the elements. What do you think the first element that we pick out is going to be? The one with the what priority? Highest priority. In general, this is kind of annoying, but in general, we use the lowest numbers as having the highest priority. It's kind of like saying, who are the top 10 teams? 1, 2, 3, 4, 5, 7, 8, 9, 10. Well, 1 is the highest priority or whatever. Right? If you're going into an emergency room, they give a 1 to the guy who's got the knife sticking on his neck. Right? So the keys determine the priority used to pick those elements. OK? All right. So that's what a priority queue is. A container has a bunch of elements. I don't care what order they're in internally, but I get to figure out what the priority of those are. Okay. Yes?
You have to remove something every time you insert.
No, you don't have to remove something every time you insert. Nope, you can keep growing it as much as you want. But the next thing you remove is going to be the one with the highest priority. Okay? It's the waiting room thing, right? 40 people go into the waiting room. The guy who stubbed his toe is fine. The woman who just was shot with an arrow is probably going to be much higher up. But they're all sitting in the same room, and they go, you next. Right? The highest priority. OK? All right. So that's what priority queues are. There are, of course, much like the other abstract data types we've talked about, they have these functions associated with them. OK? You can insert an item into a priority queue. When you insert into a priority queue, right, you need two things. You need the actual key and you need the element that it's going to be associated with. I should say you need the element and the key it's going to be associated with, right? You store the elements by their keys, and the elements themselves are what you get out of the priority queue. Turns out you can get the keys as well, but that's a different, we'll get to that in a minute. You also have the min element. Now this is the one where you're trying to find the smallest key, in other words, the highest priority. Okay? The one with the highest priority. And then there's removemin, which just removes the element with the highest priority. Okay? This should sound vaguely familiar, right? It's like a stack or like a queue or whatever, except now you get to have all the elements, and you can pick the one out that has the smallest key, highest priority. Okay? I see some people furiously writing. Don't worry, these are all online in the notes. So if you want to get those, you can. There are other functions that aren't quite as high, like necessary. These ones are necessary. The other ones are just kind of nice to have. You can have a size function. How many elements are in there? Is empty makes sense to have. The next one is interesting. MinKey returns the smallest key, which is kind of cool. Yes?
The smallest key in the queue, or the smallest key possible?
The smallest key currently in the priority queue. Yeah, good question. Yeah. Why would we care about like just telling which the smallest key is? Like figuring out which one the smallest key is. Any idea? Yeah.
If you're inserting, you want to know if it's the highest priority.
Yeah. What if you're about to get ready to get on the plane, right? And President Obama walks up and says, hey, Air Force One just broke down. I need a seat. Guess what? You better know what the highest priority is and make him the highest priority, right? Unless you're in Texas or something. No offense to Texans. But the point is that there's other times where you'll need to know, hey, what's my minimum key? It's actually, we don't have a max key function, which is interesting, right? You can't, like, because of the way data structures are, this abstract data type is built, it's much harder and, in fact, not really allowed to get the max key, right? You could build it in, but your asymptotic complexity is not going to be so great. Okay? I threw this in here. You can get what's a constant reference to a key. You don't want to change the key, right? When you find out what it is, because if you change the key, you'll never be able to find what you can't reorder them inside the data structure. So you're not allowed to change the key. You could do min element and get a pointer to the element and then change the element all you want. It's not actually going to change anything, right? The structure is intact. But if you tried to change the key, you'd be in trouble, because then your whole data structure, which is based on keys, might be out of order. Okay? Whatever you're ordering under the covers is, you're just not allowed to change that. Okay? Questions on that one? All right. So we're getting there on what these priority queues do. They're definitely simpler than your regular sequence, right? You don't care about the position. Under the covers, you might care. But as far as the data type is concerned, it doesn't matter where they are in the queue, as long as you can get the minimum one out, right? You don't have to worry about inserting before or after indexes. Forget about it. It's all like behind the scenes. We only need one insert and delete function. Kind of nice. Okay? All right. Let's do an example. So the example here is going to be basically, I'm going to insert a bunch of keys with their values. Okay? The keys are actually going to be numbers, integers, and the values or the elements are going to be letters. Okay? So we can do an insert. We can insert item 5 with the element A. And that goes into our priority queue here. And that's all that's in there. We can also insert 9 and C, which goes in there. And notice it doesn't really matter what order they're in. I mean, they happen to be in increasing order now. If you insert 3 and B, well, now it really doesn't matter. All we know is that there's these 3 in here, and they're in the priority queue. We could also insert 7, same deal. Okay, the inserting is easy. If we do min element, what are we going to get out? We're going to go find the one with the minimum, with the highest priority, and return its element. Okay? What if I do MinKey? What's going to happen? It's going to say 3, right? If I do MinKey, then 3 pops out. Right? Pretty straightforward. OK, so we've got all 4 of those in there. If I now say removemin, right? If I say removemin, then no more 3 and b. They're gone. OK, pretty straightforward. This is not too tricky. All right. Then I can say size. I could do that. That's going to be 3. I could say min element now. Min element's now going to change to 5 because it's the minimum key in there. OK, yeah.
What do you do with duplicates?
Duplicates are tricky. Yeah, good question. Nobody asked that earlier. Duplicates are tough. How might we deal with duplicates? Any ideas? What do you think, Alex?
Just find the first one and whatever the structure is and send out that one.
Yeah, you could do that. That's one model where you just say, too bad. You put more than one in there, you get the first one. Right? Same thing with the remove. You remove the first one. It's one way to do it. Other like different languages that implement these things do them in different ways. In Python, if you have a dictionary and you're trying to insert something into the dictionary and something's already in there that has the same key, anyone know what happens? What's your guess? What do you think happens? What? Good answer. It's not added. That's not true, but it's a good answer. Like that's the one. It could give you an error and say some languages do that. JavaScript may do that. I forget. Some languages do that where they just say, nope, you can't do that. In Python, it actually replaces the value. So if you tried to insert 5, b in here, it would go, OK, now it's 5b. That's all it does. Yeah.
Could you have like a third variable, like a count?
You could have a count. Sure. Yeah, you could have a count there. I mean, the problem with count is it would have to be 5a has a count. Like you couldn't do 5b and somehow count that. You could maybe have 5b, but then this is like a list, A, B, C, D, whatever, right? You might be able to do that. But it depends on how you implement it. It's not quite as rigid as some other data structures. Yeah. Yeah.
Didn't you say earlier that keys can be more than one value?
There could be. You could do that. But when you insert into here, you can only insert by one. You have to merge it into one key.
Right.
Like in other words, you can have an element have lots of different keys, but when you put it in a data structure, you have to do it by a certain particular key. That's all. Yeah.
When you were talking about the B will replace the A if there are duplicates in
Yeah.
terms of priority, does it do that for C++? And if so, like, if you're talking about the hospital waiting list, does that have some serious like not great implications?
Well, hold on. When you say does it do it in C++, we're building these, so it'll do whatever we want, right? Implications. Well, yeah. I mean, that's like saying. I mean, it's kind of like saying, well, the person with the knife wound just died. We're going to put the gunshot wound at the same priority and make that. You know, it could do that. You'd probably have them all in there, right? But it's kind of a morbid example. Sorry. Anyway, you could do. You can. I mean, it might have ramifications. Yes, definitely. Yeah. Okay. Right. Yeah. So this is one way of dealing it. Is where you say dealing with it is saying, fine. If I do 5, b, that's another one in here. And then the problem is you can't just say, give me the minimum, because it might be one or the other. You can't be guaranteed. You could write a function that says, give me all the ones at the same priority, at the minimum priority. And then it just gives you a list of all of them. That might be another way. But again, we're talking about the kind of basic structure. But you can manage it however you want if you want to make it bigger. Yeah.
Could you just do like 5 and then that be an array?
Right. You could do 5. You could do return min, and then it returns an array of various values that are 5. Yeah, whichever works out. Yep. You can make it that way. We would define it a certain way. Did you have a comment? No. OK. Any other comments on this? The example. Let's see what else we got. We've got remove min again. Now the minimum one's 5. If we do remove min again, right? Now the minimum is 9. Hey, guess what? I removed the minimum and it was 3. Then I removed the minimum, it was 5. Then I removed the minimum, it was 7. If I do remove min again, it's going to be 9. What have I just done to those values? I've sorted them or ordered them. This is one way to do sorting, right? Put everything in a priority queue, take them all out by min. Well, it depends on how you implement it, but not a terrible way to do sorting. OK, we'll talk lots about sorting later in the class when we get back from spring break. By the way, There were some comments on the midterm evals. I've been kind of going through those. I literally just got them today. Somebody said, a couple people said, boy, it'd be nice to have more work, which I thought, OK. I mean, I appreciate that for people who are like ahead. I might give you guys something to think about over spring break, but nothing will be due over spring break or due during spring break. So for what it's worth. If you're worried that, oh my gosh, I won't have a project to work on, well, I also might give you I might open the project up a little early, especially for you guys who didn't believe me that this assignment, this homework 4, took longer than it did. You might need to start earlier. OK, if I remove min again, it's an empty true. What if I do remove min one more time? Error, yeah, it blows up or whatever you say. You might write error or whatever, right? So how do you tell if it's got nothing in it? It is empty, and that would return true. OK? So again, this is not, I don't think this is rocket science. I just want you to kind of see how a priority queue works. OK? You can take things out by their priority. Put them in any order, get the next highest priority one out. The waiting room is a really good analogy in this case, right? If you've got the stubbed toe, you'll sit there for 4 hours because other people who've got much more serious injuries can come in. OK? All right. Let's build some. Here's what we're going to do. We're going to build a priority queue unordered list. We're going to do this 2 different ways. We're going to do it with an unordered list and then an ordered list. OK? And we're just going to have this struct called the priority object. And it's going to have 2 things in it. And you can guess what the things are. It's got a key and an element. In this case, the key is going to be an int. And an element is going to be a string, just like the example we gave. The code for this is all on the web page under today's lecture. So if you want to go look at the code because it's too small on the board or whatever, or you just want to look at it, by all means, download that. OK? So that's what we're going to start out with. OK? All of these abstract data types are going to have some sort of public functions. OK? Whoops. The public functions here, well, we've got a capacity. This is part of the fact that it's just an array that we're using. You've got a size, which is just going to return the size. You've got isEmpty. You've got insert item. Notice insert item has to take a key and an element. You get a min element, which has to return a string because elements are all strings. You have MinKey, which returns an integer because our keys are integers. You've got remove min, and you've also got print the priority queue, which we won't write today, but it's in the online zip file. OK? So these are the public ones. Privately, we can have some other ones. We've got the actual array, right? We've got the size, we've got the capacity, because we're using arrays. You could implement this with a linked list. That's fine. We've got expand, and we've also got a private function called minindex. Minindex is going to return the index in the array of your element. It's not part of the priority queue, because as far as the person using the queue is concerned, it doesn't matter that there's an index there. All it cares about is remove min. The fact that you internally want to keep an index of where, like, you want to find the index where the minimum is, that's a different story. OK? All right, so those are the functions there. Let's write these functions. Let's do insert, or some of them. Insert item. If you're inserting into an unordered list, it's pretty darn easy, right? You've got an array. And you insert at the end of the array, insert at the end of the array, insert at the end of the array. That's it, right? You basically just say, fine, insert at the end of the array the key, and then at the end of the array the element. And that's it. Right? Pretty straightforward. What's the asymptotic complexity of this? Constant, right? Woohoo! That's good, because it's easy to insert into an unordered array. We're going to have to write the removemin function, right? But before we do that, we're going to write the min index. You'll see why in a few minutes. To get the minimum index, before you even look at this code, think about what you have to do. If you've got an array that's unordered, how do we figure out which one is the minimum? Yeah. You go through the list. Now, can you stop at some point when you hit the minimum? You can't, right? Why? You don't know if it's the minimum yet, right? So you have to go all the way to the end. So this is all I'm doing here. I'm basically starting out and saying, look, the minimum 0, because it could be. And then we're starting it, doing a loop from 1 to the size of the array, well, less than the size of the array, and comparing the elements to each other and saying, are you smaller than you? If the next one is smaller, because remember we're trying to find the minimum, if the next one's smaller, or I should have said less than or equal to here, but if the one that you're looking at is smaller than the one you've already got, right, then you change the index to the one that you're now at. So then you go through all of them, and at the end of that whole loop, you'll have the minimum index. OK? Asymptotic complexity of this. Linear, right? So linear gets a boo, because we don't like linear ones. Not too much anyway. OK? To get the min element, you just call priority queue. You return priority queue at the min index. OK? This is the public function. This is the private one we're calling. And you return the actual element. Right? OK. Removemin. And by the way, MinKey is more or less the same thing, except you return the key instead. Removemin. What do you have to do before you remove the min? Find it, right? It's going to be in there, because unless it's an empty queue, it's going to be in there. But basically, you first find the min index, right? And there's 2 ways to do this, right? There's 2 ways to return or to get rid of the min index. Let's say that we've got 5, 22, 9, 17 in there. OK, if we find this one, what's one way we could change this so that the array is proper after we remove 2? Winona?
You just, from 2 over, you move like 9 and
Yeah, you move 9 there, and then you move 17 there. And that's asymptotic complexity of what? Another n, right? What's nice is, well, actually, yeah, you have to, it's basically could be up to n squared, right? Things that you move. Because you have to find it first, then you have to go through and move everybody. If you do it right, you could do it kind of as you go, but we're not really, right? What's a better way to do it? Which is what I do up here, actually. Yeah. Yeah, just move the 17 over there, because if it's unordered, who cares where the 17 is in here, right? We know it's unordered, so we don't care, and that's only one swap. And then we just make the size stop here, and we're good to go. OK, does that make sense? It's just a simpler way of doing it, and it makes it so you don't have to walk through the whole list again, or rather move things in the array. OK, so doing this whole function is going to be what asymptotic complexity? N again, right? Why? Because you have to find it first. Right? Either way, you're going to have to find the min index. OK. This came up earlier in class. Is there a way to do better on this with the min index thing? Any ideas or questions about it? Let me pose it to you this way. Instead of having min index be a local variable here, what if I made min index a class variable? And every time I insert it, if it was the minimum, I just made that one the minimum. Would that be good?
Wouldn't you have to search through it every time anyways?
Wouldn't you have to search through it every time anyways? Almost. You would, yeah, go ahead. What were you going to say, Al?
I was just going to say you could, if you're storing it every time, you just have to compare them in the min, the one you're inserting in. Every time you insert, you just have to compare to what you already have there.
Yeah, but then you're going to get the min, right? But what's the issue? I think you were going to say, Nate? No? OK. If you do this, if you did that, that would work for one remove. But then once you've removed the min, what's the next min? What do you have to do to find the next min? You go through the whole thing again, right? So you get the benefit of doing it like once if you try to do that. But then the rest of it's done. Now, so part of my PhD thesis was in parallel computing, right? Doing things in parallel. It would be kind of cool if you wanted to do that and keep the minimum, and then return the minimum. And while the user's doing something else in the background, like in parallel, go find the next minimum and put it in that min value. That would maybe save some time. You would lose, you wouldn't gain anything if you went remove, 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 right? because you don't have any time in the background. So you have to wait for it to go through everyone at once. But that's you're not actually gaining anything by doing that. Yeah?
Could we build a priority queue out of like an AVL tree or a binary search tree?
Sure.
That'd be lovely.
We could do that. We'll talk about that after we get done with this one. We'll sketch that one out too. Yeah, that one's not too bad. That was not too bad. OK. All right. So let's see. So this is not so great. Well, but we did it, though. We made our priority queue, and it works. It's not the best behaving in the world, asymptotically speaking, but it's not too bad. Let's switch it up now, right? Remember, when we inserted into the priority queue in the when we search through the priority queue for an unordered array, it takes forever because it's it's a linear search. But if we do this into an ordered list, well, then the searches will be really fast, right? Because we can do a binary search through an ordered list. OK? So let's keep the key list in order as we add keys and elements. OK? Here's what I want you to do. I want you to talk to your neighbor about this. And what I'm going to ask you to do is think about having an array. Let's call it, let's do this. Well, we can make it 5, actually, whatever. It was whatever the same. 22, whoops. It's got to be in order now. Let's say 50 and 67. OK? If I want to insert into this priority queue, how am I going to do it in this array to keep it sorted? Talk to your neighbor, figure out an algorithm, and then I'll ask you guys. OK? Take a few minutes to do that. Let's do this.
How much value can you get out of changing the starting value when you're doing a binary search? If you're going through an array.
Changing the starting value.
Like instead of starting in the middle, say, starting at the priority number divided by the number of elements in the array. Rounded.
It's a good question. I don't know. I think it would totally be dependent on what the data in there is. Because remember, you can always come up with a case where that calculation is not going to make a difference, right?
Yeah.
But yeah, you'd want to. It's not a bad idea to look at some of the heuristics like that. I don't know that you'll ever gain much, but maybe something.
Bigger or smaller than it, and if it is, you go you drop like the half bigger one. So if it's already done ordered. Yeah.
Yeah. Mm-hmm.
How would we deal with duplicate keys with different values? Would there be like a middle pointer or something? Is there an easy workaround for that, or?
I don't think there's an easy one. But yeah, you could change it a little bit. Yeah, you could change the node structure to it. OK, who thinks they've got it? Just quiet down a little bit. Let's get somebody from that corner of the room who hasn't talked lately. Yeah, there you go. Yeah, go ahead. One of you guys up there.
Well, you would kind of just go through and see when you had a number. So you would like make a loop and say.
Let's say we're going to insert 37 into this.
You go and so by the time you got to 22, you would see that 37 is greater than 22 or less than 50.
OK.
So then you would move 50 and 67 over.
OK, I like it. So you're saying go until you get to what's between two. Let's make it a little more clear, right? Let's just start at 5. OK. And we're checking 5 against 37. So 37 is greater than 5, so what do we do? Go to here. So 20 is less than 37, so you go here. 22 is less than 37, so you go here. Then what? 50 is greater than 37, so what happens?
So then you would say everything now to the right of that would be moved over one index.
OK, how do we do that?
You would say, what's the name of the queue? Like, there's a
PQ.
So P would get, so PI would get PI plus 1.
So this one would get this one?
Oh, no, so it would be minus.
Sorry, this one would get this one? OK, so then you change 50 here, and now you've got 50, 50. And then what happens?
Oh, yeah, you have to start that.
Yeah, you'd have to start from the end, right? It's a better, you can do it from the front, but then you got two, you're going to have to have 2 for loops, right? Or do something wacky in your for loop. Let's start from the end, right? And start at 67. And 67 says is greater than 37. So what do you do with 67? Move it here, right? And then you, well, actually, it's still there. And then you go to 50, and 50 is greater than 37. And then you go to 22, and 22 is less than 37. So 37 goes there, right? Does that make sense? It's called an insertion sort. It's one of the sorts we'll learn a little bit later. OK? What do you think the asymptotic complexity of that is? What is it? Linear, right? Because you could have to go all the way to the bottom, all the way to the end, and move everybody over once, right? But you only have to do that once. So inserting in this fashion is linear. What if you were inserting n items? What would the total asymptotic complexity be? N squared, right? Because for every element, you have to do up to n different movements. So it's going to be n squared. Yeah. So insertion sort is not a particularly good sort. OK, it has a best case of what? What if I was to insert 80 into this? Constant, right? Best case is constant. Worst case is n squared. OK, we'll get into a lot more details about insertion sorts later. OK, all right. So that was good. That's how you do an insertion. Oh, man, this font is tiny. Sorry about that. So here's what's going on. Here's the pointer for this. Here's what's going on in this. We're just doing exactly what you said, right? We're basically saying this is the insert item. We're basically expanding if necessary. We keep it ordered. We basically go through the list, right, and walk backwards and move the keys one at a time if they're greater than the priority that we want. Move them, and then break. You could do this stuff inside this statement here. It's fine. I don't know why I didn't. But you could actually do the changes up here. And then make sure you increase the size of the queue. Yes?
What if you want the array sorted in reverse order so that the smallest is at the very end?
Yeah, this is a good point. Am I doing that here? I think I am doing that. The minimum is probably going to, it should probably be backwards here, right? It should probably be the minimum one is over here because removing is easy, right? Remove, and we'll get to that in one sec. Yeah, so it's better to have it backward, like the other way. And it's just a matter of changing one thing here. This is, I think, the correct way, right? But this is still order n, which is not really what we like. But to get the min index, if we do it like that, if we have the minimum one being up here, if we ordered this exactly the reverse, isn't the last one in the priority queue going to be the min index? What's the asymptotic complexity of this? Constant, right? Woohoo! That's what we want, right? We haven't changed this at all. We're still finding the min index. But the min index always happens to be the queue size minus 1, because it's the last one in the array. OK? All right, so that's nice. Remove min, also simple. In fact, so simple it's almost like you can't even see the function here. This is all error checking. You're just moving you're just making the size less by 1. You're done. It's removed. Right? So that's nice. What's the asymptotic complexity of this? Constant. Woohoo! OK. All right. So now we're to a point where we can compare these guys a little bit. The unordered list has a complexity of 1, a constant for inserting, but taking the min element and removing min are both linear. The ordered list has a linear insert for each element, but doing the remove min and min element is constant. Which one's better? Unordered list or ordered list? Totally depends. Do this. Talk to your neighbor. Figure out why some of you guys think it's the ordered list, some of you guys think it's the unordered list. All right. Who wants to tell me when you might want to use an unordered list over an ordered list? Yeah, Katie.
If you were only ever expecting to take the top like 10 priorities.
Yeah. If you have a list and you're putting a billion things in there, and then you only need the top 10, maybe sometime later or whatever, yeah, you probably want to use an unordered list, right? Because using an ordered list, you're going to spend so much time ordering everybody for a benefit of a tiny little bit at the end.
Like you were putting in time for the Boston Marathon and wanted to give out prizes to the top 5 people.
Yeah, this is a great way to do it. Yeah, that's a good point. You'd want to do it this way if you had to do a list for this, because if you were giving out prizes for a race, because you only want the top so many people get prizes, right? You don't care about the rest. So yeah, that's not a bad idea. Okay, conversely, when might we want to use an ordered list? Yeah.
If the data is constantly shifting, or you're inserting and deleting a lot of people all at once. So say a hospital priority queue, where you are constantly adding but you're also deleting them just as quickly.
Yeah, I suppose deleting them and adding them just as quickly. I mean, you've got a benefit of you do have the benefit of O1, but you're still going to be n squared in that case. Yeah. What do you think, Nathan?
Maybe if you're inserting them over time, but you use them all at once, then it matters more for
If you're doing the, I mean, I was thinking a little bit more broad than that. Like keeping things in order takes a long time, but then what happened now that it's in order? What if you want to do what? Remove lots of things. What if you want to keep removing like you're going to remove everybody in the queue at some point or whatever? Maybe then, and this is kind of what you were getting at back there, but the idea is if you insert all at once and then it's already sorted, then you get lots of benefit if you have to do a lot of this stuff many times at the end. Okay, so there's trade-offs here. Definitely trade-offs here. Okay, yeah, Tafari.
Be the same like thing, but I remember at least like in older Windows computers, there used to be a thing like if you open like the Windows Explorer, it would be like, oh, like I haven't indexed everything yet, like I'm indexing things.
Yeah.
I feel like a system where like you could just like was it just like inserting things into the computer and like later when it has downtime it would go and put everything into an ordered list.
Yeah, you could definitely do that. Yeah, you could create a hybrid sort of thing where you say, if I'm not doing anything else, I might as well go and order things. Yeah, you could probably do that. And that's not a bad idea. And you're absolutely right. I mean, Windows in the background is going to sit there and chug away indexing, but it's not going to stop you from doing other stuff, right? Unless you're trying to play some game or something and you don't need all the processing. But yeah, that's good. OK, all right. I promised you we would do a priority queue with a tree. Let's do that. What kind of tree? A binary search tree? Not just like some other tree, right? Binary search tree? OK. So if we're going to insert into a binary search tree, what do? Just insert, right? 10, and then if we inserted 4, and we inserted 20, and we inserted 0, and then let's say 6, and we'll do one more. How about 40? OK, there's your binary search tree. OK, what was the asymptotic complexity of each one of those? Log n, which is pretty good. Woohoo, we like that, right? Log n. It's going to be a little more tricky to do an AVL one. For anybody who tried to do an AVL tree, right? You do have to do rotations and things, and it's a little painful. You still, in the end, it's logarithmic, so that's good. OK, but it's not the easiest thing to write, right? I mean, you do need a binary search tree in the background, but you can totally do it this way. OK, what's it going to take to get removemin? What do you have to do? Find min, and then remove. Right? Find min and then remove that element. So that's going to be logarithmic, and then it's going to be another logarithmic, but really that's just logarithmic. So two logarithmic, but it's more or less logarithmic. So that's not too bad. OK, so that's actually not bad. So binary search trees are pretty good. They would probably beat out both these methods. So not too bad. OK, question?
But once you start deleting the binary search tree,
Yeah.
don't you have to start, like once you get past 10, doesn't it just turn into like removing the root and then doing like...
Yeah, you're probably going to eventually get some non-logarithmic behavior in there if you try to do the whole thing. You're right, because this is inherently ordered, right? I mean, it is ordered in the sense that you've got the left tree would be gone if you're removing element, and then you got the whole right tree left. Now, in the end, it's not too bad, but yeah, the behavior doesn't doesn't lend itself that well to it. That's a good point. Same kind of comment or what?
No, I was going to ask what to do with duplicates.
Same thing, you'd keep a count, whatever. I mean, it's just like you could do with the homework, but we could do that. We're going to see on Wednesday, like I said, this whole lecture was basically set up for another type of structure, data structure actually, that similar to this, but actually more efficient. Okay, so you'll see how it works, and it's actually a very cool data structure. Another one of my favorites. I would say tries are probably my favorite, but the other ones, this one we're going to talk about on Wednesday, pretty cool. Okay, all right. Other questions on priority queues? Anybody else? Kind of get the idea. That was a lot of stuff to talk about it, but I think you get it now. Priority queues are how they work. Okay, all right. So good timing. We are done with priority queues. I think the rest of the stuff is just the reading and the references. What I want to show you briefly is this font going to be big enough? Maybe a little bit bigger. Maybe that. OK, let's see. There we go. Homework. What I want to show you is how many people were able to use GDB for some of their projects. OK, good. For those of you who, and by the way, if you're using like the Eclipse debugger, it uses GDB under the covers. So you're using GDB, you're just using it in a slightly more friendly way. OK? I'm going to show you a little bit about how to use GDB directly, just so you get the feel for what kinds of things you can do. In hindsight, I probably should have showed you this before this project with homework 4 was due, but you'll be able to use it for future ones. And if you get to Comp 40, you'll want to use this pretty frequently. So thought I might show it to you. OK? So I have homework 4 solution, which too bad you didn't hack into my computer. Would have gotten that. If I do make, it will make it. And then let's see. If I do if I do GDB, actually, let's just run it first. Homework 4. I think this is the main one, I think, right? If I do GDB, everybody see that in the bottom? Let me move the window up a little. Whoa, that's not how I do it. Hang on. There we go. There we go. OK. It'll be up there. All right. If I do gdb./homework4, it will load it in. And by the way, when you do the -G, when you're compiling something, that means give more information to the program so that it can do what we're about to do in GDB. OK, so watch this. If I do L in GDB, if I type L, it will list out my program kind of around where it's going to start. This is the beginning of my program. It's actually going to start at line 25, because this is the first line in our main function. OK, it's going to start there. And if I keep hitting return, it will do the last command. So I could do L again, but it'll do the last command. And just keep going down here. Let's go down to our remove function. Let's say I want to run the program and stop on the remove function. It's pretty easy to do in GDB. You just do what we call set a breakpoint. Anyone know what the letter is for breakpoint? B. Breakpoint on the line you want to go to and stop before that line. So if I do B44, it will stop on this line. It'll do everything else, and it'll print everything out too, but it'll stop right there on line 44. So it will say breakpoint at line 44, and then if I type run, it will run until it does that. And notice it printed out all this other stuff. It printed out the tree. It printed all this stuff out. OK, this is what our tree. You guys are probably really sick of looking at this one right now. All right. Remember, so there's a 4 there, 2 to the left, 11 to the right, et cetera, et cetera. OK? All right, so we're in the program, and the program's waiting for us to do something. And we're on line 44. If we want to go into line 44, we have to do what's called step into, using S for step, right? If I type S, it takes me into my binary search tree file to the public remove method. OK? Sorry, I'm in the public remove method, and it's about to call the private remove method. So if I step into that again, OK, it will now go in here, and it will be in our private remove method, which you guys are also probably pretty sick of looking at. And it tells you what the values that got passed in are. Parent was null. Value was 9. Right? There's the node and so forth. And that's kind of cool. Yeah?
So, technical question.
Yeah.
When I was trying to debug something with GDB, I got that far, and then as soon as it something that I think it was, as soon as it hit something involving a string, it went crazy and no amount of hitting S got
Yeah, if it hits a string, you have to step out. I think it's return, I believe you type. You have to step out. You have to return from that function. I think you type the word return and it goes back, I believe. You have to look it up. But basically, we're now inside this. Now, we can print stuff out ourselves. If we do print, or P, and then type node, arrow data, it tells us that the data is 4. And if we do node, arrow left data, what do you think that is? It was 2, right? I think it was 2. Because, whoops, what did I do? Oh, thank you. I forgot the P. Thank you. P, node left data. There we go. It's 2, right? Which is what it was in the original tree up here. Bing, there it is. The left of 4 was 2. Hey, it looks like 2 has a count, right? So let's do P left count. Yep, it's also 2. OK, so you see how you can get real data in here? What's neat is you can do, let's list the program. OK, we're trying to find, let's put the value for a sec. The value that we're looking for is 9, which if we looked for our tree, it should go to the right to 11 and then to 9, right? So what we can do, I don't know, let's put a breakpoint right on line 140 again. And now there's a breakpoint on line 140. If we say continue, it will go into the next one. And guess what? Let's see. We are now on the line that we came to. And if we print out our current node data, node data, that will do 11, because what did we do? If we're looking for 9, we went to 11, right? And you guys are like used to seeing this, thinking what's going on. And then we're going to go left to 9, because we're trying to remove 9. So if I run again, if I do continue again, it will take me there. And if I print out the data there, now we're at 9. OK? So now we're at 9, and you can do that. Now, what's neat about the next thing I'm going to show you is, so remember our call tree here, right? What do we have so far? We've got main called remove the private function, called remove the public, or sorry, remove called the public function, remove called the, or then that one called the private function, this one called the private function. On, let's see, that one was the root, which was 4, we'll say. I'm writing too fast, sorry. We've got 4, and then that one called 11, and then this one called 9. Well, what if we want to go back up and look at some of the things? You can actually do that with the up command, right? So right now, if we're printing the data, it is 9. If we go up, the data was 11. So up means go back to the previous call stack and see what the data is. It's 11. If we go up again and print the data, it will be 4, because that was what our tree looked like. So you see how you can see the whole state of your program now? It's really pretty neat. And then you can go down again and down again. And I don't think you can go down. Yeah, it says if you're at the bottom, it says, hey, you're at the bottom. Don't go down anymore. And you get more information about the program. Yeah?
Just like a question on how GPU works. So if I was in a while loop and I kept hitting continue, would I just stay in the while loop?
You would stay in the while loop. Yeah, well, it depends. If you hit continue, if you have a breakpoint in the while loop, you will go to the breakpoint. So if the breakpoint's in the while loop, it'll go back to that breakpoint, back to the breakpoint, back to the breakpoint. Yeah. If you just hit continue, if I hit continue now, it would probably end the program, because there's no other breakpoints before the end of the program. Yeah. OK. So you can do that. Unfortunately, you can't go backwards. You can't undo state. That would be cool if you could. You can't do that. As far as I know, you can't do that. You can do some other cool things. This is actually really neat. When I was sitting after class with another student, and he said, can you do this? And I said, I don't know. And we checked, and you can. What if you call, let's see, what's the name? It was called, was it called find min and find max? What's the min and max of this tree? The max was 15. Let's do call find max. Do we need to pass in the, no, we don't. That's it. Call find max 15. Right? It just returns what it returns, which is kind of neat. If you want to call stuff while you're doing it. Oh, hey, what if I want to print the tree, right? Was it print tree? Call print tree. Like that? I think so. There you go. All right. And you can do it while you're debugging the program. That is pretty cool. Yeah. You have to be at a break. You have to be stopped. Yeah, you have to be stopped to do that. Yeah. I think technically there's a way to change the program while you're debugging it, but it's much harder. Like I don't know that that's something you'd want to get. You might have to do it in assembly language. You might not be able to do it in the thing. Yeah. Yeah.
There's a workaround to do that easily. You just have GDB open in one tab and you
Yeah.
have things open up in another.
Well, right, but then you have to rerun it. Like you have to reload it. But you're right. That's pretty simple to do. Yeah. So you see how the GDB can be pretty helpful for these things, right? Being able to call, print the tree at any stage of the game is kind of neat, right? You could go and do this. So there's lots of ways you can use this. I would suggest, if not learning the Eclipse one, then definitely learning the command line version, because it's pretty helpful. Okay. All right. Any questions on all of that? All right. One comment I got for the midterm reviews was, I keep forgetting to do the pre-lab. Anybody keep forgetting to do the pre-lab for their labs? Don't forget tonight. Okay. I forget what the comment was about. It was like, please post that the pre-labs are available or something. So I'll do that. I'll start doing that. All right. I'll see you guys Wednesday.